Can you open the chat
Yeah.
over there maybe also? And
Yeah.
then, oh my, oh yeah, look at that.
All right, it's beautiful
Look
in the
at
chat
that.
now, right?
Wow. So, very professional. Next time we start here, I think it'll be really good.
I think that'll be good. Yes, next time.
Well, thanks so much for joining the DevOps stream. Sorry, the Dev Update number 2. We're basically number 3 now because we just spent number 2 on setting up OBS, but it's all good. Like I said, we're gonna go through Hyperswarm week 5 today. It's gonna be awesome. We're gonna do some demos. Now we know how we can share the screens. We can do the demos. It'll be great. Now, surely the demos will all fail because it's like that's
how it's gonna go. Yeah. That's our luck.
I'll be fine. I'll be fine. We made a little presentation for you. So let's dive into it. Yeah, it's me here and Andrew. If you just joined, if you haven't been around for 20 minutes watching us setting up OBS.
Yeah. Hello.
So we'll go through a couple of things, 3 things. If you don't know, the current version of Hyperswarm, which is the first actually super stable one that's running, is called V4. It's been serving us well. We love it. We are improving it though, so we'll talk a little bit about why we are improving it and how. That'll be the main thing. And then obviously we'll spend tons of time on demos, and we also have time for a little Q&A at the end. If you want to know anything about setting up OBS, we can answer that also. We have all the skills. So yeah, diving into it. So like I said, Hyperswarm V4 is the current version that's deployed of Hyperswarm. If you don't know what Hyperswarm is, it's basically like the network glue that links the hypercores together. If you use the hypercore protocol, people also use it for other things, but basically like our networking layer. It's one of the powerful APIs we have combined with the other ones. So what we really like about Hyperswarm in general, especially in V4, is that it's one of those things we make where we spend tons of times, but at the end of the day, it's like a 10-line API with a couple methods. So it's super powerful, but like obviously has tons of stuff underneath. It's like just the tip of the iceberg, but in a good way. We can expose it in a way where it's very easy to understand. It focuses a lot on this thing called hole punching. Hole punching is the technique of connecting computers on home networks, so you don't have to run servers. It's very important to peer-to-peer. That was the first part of our stack to actually introduce serious hole punching. And if you ever follow anything we say, we just say hole punching more and more, because that's the name of the game these days. It's also, and especially through community contributions, it has a very easy to use CLI that makes it easy to debug and interface with the swarm, and also like set up nodes to help run it, like DHT nodes and stuff like that. And that's been very helpful, and we love it. And then finally, actually, I don't know if people actually know this, but there's pretty great capacity on a network. So roughly at the moment there's, and it goes up and down obviously, but there's between 1,000 and 2,000 nodes already running. And these are just nodes that are like helping serve the routing of the traffic on the network. The traffic here being just the discovery part. Obviously, the rest of the traffic goes peer-to-peer. So you're watching the chat, I guess?
Yeah. Awesome. In the chat, if anybody has any questions, by the way, I'm watching the chat over here, so ask away.
So yeah, so we love V4. It's great. Kind of looks like this. That's what I meant by simple, powerful API. It's just like a thing you make, and then you can join a topic. Topic is just like a hash or a key or something, and then you get connections coming in on that. And yeah, it's pretty simple. And you know, that's basically it. And this is like very powerful, and we love it. And like I said, that's like the power of it. So we've been thinking about and talking internally about like improvements for this in a while, and especially also with a lot of Discord community people in our Discord. There's a Hyperswarm channel there. So one thing we're always looking for is like just, you know, making hole punching better. Hole punching is one of those magical things. When it works, it's just amazing, and often it does work, but like there has been times when it didn't work. I'm sure people who have played around with the swarm have had some situations where like some network thing made it hard to use. So we're always looking for solutions and always reading papers and like how we can improve that. And we'll talk a lot more about that. We've also been wanting to. This is one of the things we actually like one of the corners we cut a little bit early on. We've been wanting to do better DDoS protection in the DST in general. So what that means is like just like there's improvements you can do to make it harder for a big attack to like try to make discovery hard in the network. And there's also papers here we've been reading that we've been implementing. That's like just nerdy, low-level stuff that most people don't have to worry too much about. Then we think a big improvement we've been adding to make it just easier to use the swarm is that we're moving the encryption layer for the protocol down into the swarm. Right now, the full encryption layer is actually running in the hypercore itself, in the hypercore protocol. And the swarm just returns like what we call raw sockets, which just means like a TCP or a UTP socket. And then we've been wanting for a while to just move the encryption layer down because that makes the swarm actually insanely powerful to use by itself because you have like the no-brainer, it's encrypted, and you can verify who people are, and you can't really use it wrong. And then in general, we always, every time we're doing anything, we're always looking for improvements in terms of like how can we actually make things faster, like discovery faster, development faster, faster.
But to be clear, the network encryption isn't moving out. It's still possible in Hypercore if you're not using Hyperswarm, for example, to create a replication stream that would be noise encrypted. But we also want to have that supported in the swarm.
Yeah, exactly. We just want to don't have any layers in our protocol anywhere where you can like accidentally do things that are like not encrypted or verified. So it's just an API improvement. Awesome. So I made a little sub expansion here about hole punching because I love hole punching. So I said this a couple of times, but like hole punching is basically just a term or technique for basically tricking, some might even say hacking firewalls into accepting connections. So if you don't know, if you have a computer at home and you want to run a server here just means like a little program that accepts connection from the outside, doesn't just like connect to somebody else. That's actually incredibly tricky because firewalls and ISPs and all this kind of stuff have all these firewalls in place that makes it really, really hard to accept anything. They'll block it. So hole punching is a huge field of network computing about doing all these weird things that somehow make your firewall think it's actually sending a request out, but in reality it's accepting a request in. And we could talk about multiple hours about what hole punching is and the history and all that, but we'll skip a little bit of that and just talk about the meaty parts because that's the cool fun. But basically, if you don't have hole punching, you don't have peer-to-peer. There's no way you can run anything from home. Back in the day, it was a little bit easier, but now with the growth of the internet and like firewalls and exhaustion of IPv4, and even with IPv6, it's just really, really hard. So it's essential. It's the most important part. If you don't have that, you don't have anything. So we've been very, very focused on always making that better. So in v4, the current deployed version, that's using something that here called like classic hole punching. Classic here just means if you ever read or watched some talks about hole punching from like the last 10, 20 years, it's a very simple technique, simple in a good way. It's like simple to implement, but very powerful for doing hole punching. And it's been serving us really well. But in v5, we're moving to a completely rewritten strategy with a ton of novelty in there that uses something called a statistical approach, where it collects a bunch of stats internally, like just on your computer, to figure out optimal strategy for hole punching all kinds of different networks. And turns out that's insanely powerful and gives us really, really good network penetration. So hooray for that. So to sum that up a little bit in like terms that might be a little bit easier to understand. So basically, when you do this classic hole punching, you're connecting two peers. There's one peer on each side, A and B. And in a classic hole punching scenario, you require both of those peers to be on friendly networks. So what do I mean by friendly networks? Here I mean it has to have a quality, the firewall, where it's like somewhat predictable what's happening. So if you ever use Beaker or use the Hyperspace CLI, they all expose this property called hole punchability. Beaker is actually the little fun little icon up in the top. And that tells you if your network is friendly. And we'll get to that in the next slide, but like most networks are actually friendly. And in the v4 one, hole punching worked if both peers were on friendly networks. With our upgraded statistical approach, We're actually taking that one further, and now we only require one of the peers to be on a friendly network, and that has massive implications in terms of connectivity in a good way. So that's really awesome. It's also much more complicated to be transparent, but it's fine to eat some complexity here because it's so much better. So just to give you an idea of like the powerful approaches here. So some napkin math. So basically, in the past we had a lot of people submit statistics, and there's also studies online about like the friendliness of firewalls and networks globally. And roughly, if you just collect data and you put all the data in one bucket and looked at it, it's like turns out around 90% of networks are roughly friendly. Now we can't really say like that. It's a little bit unfair because networks are not uniformly distributed. Like if you're on a friendly network, you're always on a friendly network. It's not like it changes every time you restart your computer. So the math is a little bit unfair, but it's fine because it makes it a little bit easier to reason about. But basically, and you probably experienced this if you used Hyperswarm today. In general, it works really well, but if you're on a corporate office or like a university or like one of those lockdown hotel networks, it tends to struggle if you're connecting to peer-to-peer, not to like open servers. And that's because those networks are unfriendly. So if you do a little napkin math here, that's what I try to do here. You can kind of see if like, if 90% of networks are friendly and V4 requires both of those to be friendly, you can just, multiply those together and you get roughly 80% out, which means that it will work uniformly in 80% of cases. Now again, that's not true because again, if you're on a friendly network, then you just require the other person to be on a friendly network, and if the other person is on a friendly network, then it's 100%. A little bit hard to do statistics here, but like you get the idea. It's like the flip side of that is if you're not on a friendly network, it'll never work. So then it's like 0. The cool thing about V5 is that we flip that around and say now it's just one of them that need to be friendly, and that massively increases the uniformity of the chances. So then you just gotta subtract the bad case, and that means it's roughly 99% of cases where it would work if this was all uniform. But the flip side of that is that if you're on a friendly network, and chances are you probably are, it's always going to work, no matter to which computer you're hole punching to, if it's into your office or whatever.
Got a question from Ben asking, are mobile phone connections usually friendly or not?
That's a great question. It depends. We actually collected a bunch of, again, open stats, and we're writing a little stats program to help even collect more stats in general. So if you want to opt into helping us, we would love to get even more data. But yeah, it depends. So in the Nordics, where we are, Scandinavia, all of the networks, mobile networks are very friendly. If you're in Germany, I noticed they're very unfriendly. And then if you go to Spain, they become friendly again. So it really depends on the ISPs you're in. So the cool thing here is that here on my Nordic phone, that's friendly. That means I can hole punch to anybody in V5 on my phone. And if you're on a German phone, even if it's unfriendly, you can hole punch still to me because I'm friendly, or any other friendly computer. But you might have trouble there hole punching them into your office without going through a relay. But the cool thing, if you just look at these stats, is that you can always turn this up to 100 always if you have a relay. It's not something we have right now, but it is something we're working on. Just uniformly, V5 only requires a relay in 1% of cases, where the other one uniformly would require it in 20% of cases. Again, take those stats with a grain of salt. So it's really good. Keep the questions coming in. We'll take them as we go along. So just to sum up, what's really, really cool about V5, and the whole reason why I actually invested anything in this in general, and I finally pulled the plug on it, was that V5 actually gives us the ability all of a sudden to run peer-to-peer networks from hotels, offices, mobile phones, if other people are on the friendly networks. Which basically means it's the first time for real you can have a computer at your home and serve the world. So if you're on a whole punchable network, you can serve anybody in the world. There's like similar to if your computer was on Amazon or whatever. So like we're bringing the cloud home, which is like insanely cool. It has massive implications, obviously, in a good way. So really, really excited about it. And we've been testing it around the last month, and
Martin asks, how can we contribute data And I imagine you mean just like networking data about your firewall at home, and if you're on a friendly network. We're making a tool to do exactly that that we'll be distributing pretty soon, I think, along with the beta release of this stuff.
The beta is already out, but
well,
probably on Monday, I would say.
Yeah, very quickly.
Because it's just a tiny little tool. Like obviously we've been testing it manually, but we just want to get more and more data so we can also for the future make it even better. So shifting gears a little bit, I just wanted to mention this. So I mentioned before the DDoS stuff. So this is only if you're like DHT nerdy, but V5 also updates the Kademlia to use parts of this paper called Secure Kademlia or SKademlia to better protect against Eclipse and Sybil attacks on the DHT. It's not something we've seen, but it's obviously something you can do and has been done on, I think, on the BitTorrent DHT to DDoS traffic, like stop discovery if you're an unfriendly person. So instead of using user-picked IDs for routing IDs, right now we're using this really cool technique where you just use a hash of your external IP and port, and that's the routing ID. And we've done a ton of stuff around that to make sure that it just works. This one is really cool because it means it's really hard to pick your ID because IPs are scarce. We're using that as a feature. It's like proof of IP. So it makes it very hard to position yourself in a specific way. It also, flip side of that is that it turns out it makes our, because now we don't need to send an ID because it's just implicit from an IP, it makes our payloads much smaller, which matters to this layer here. So in general, just makes it much faster. Well, not faster, but definitely faster. So that's all I have about this. I'm happy to nerd around with that. Somebody wants to know more, but it's just more like it's also just security nonsense. So don't want to spend too much time on that. Just saying it's better. Yay! And finally, like I said earlier, everything is now always on the connection part end-to-end encrypted, meaning that when you get connections from the swarm, they're always authenticated and encrypted using noise, and you can always know exactly what key pair was used to make them on both sides. And that also means that we're actually getting completely abstraction-wise rid of IP and port for peers. Now it's just all peers always a key pair, which means that when you do announces to the DHT, that's what that join thing does. It does something called an announce. Instead of saying, hey, I'm an IP, it just says, hey, I'm this public key. And then it has a signed proof of that. So that's the low-level abstraction now, and it's really fun and really nice because it allows us to make these very powerful additional APIs that are pretty low level. In addition to the Swarm one we showed before, the classic one, that's just like here's a bunch of connections. So I have a little example of that here. So basically now, and this is on the DHT layer, that's kind of like the raw networking layer now. And this is already released as a release candidate. I'll start that in a second. So basically now, you can make a DHT node, and on that node you can create a server, and you can make many servers. You may have many servers you want. A server here is just conceptually similar to an encrypted TCP server in Node. And then you can listen, but instead of listening on a port, you listen on a key pair. And the key pair here is just a cryptographic key pair. It's just a secret key and a public key. And the secret key, obviously you want to keep secret, and the public key is your address. That's the thing other people can use to call you, similar to an IP in a port. So this is what a server would look like. You can see here as a connection comes in, you can see who came from, their key, and obviously it's all verified by noise and secure and blah, blah, blah. And everything you send over the socket is secure and authenticated and encrypted. And then similarly on the other side, similar to the Node API for TCP, you can just connect, and so you just have the other person's public key as a buffer, or you and data array. And you connect to it and you get an encrypted socket back, and you can just write messages to that one, they get relayed to the other one, and we have a little event here that's...
A question from Paul actually about how does the pub key map to IP and port once it's, because the pub key is what's stored in the DHT.
Yeah, so it's a very interesting question. It's one of the most novel things we do. So basically, in this previous example, what happens here is that the node, and this would run on a computer at home, right? Would take the public key, it would hash it, it would do a lookup to the DHT, find nodes that are close to that hash. That's how DHT routing in general works. So query the DHT if it's like a million or 100 million or 1,000 peers, doesn't matter. We'll find peers really fast that are close to that public key. Then we'll pick a couple of those and say, hey, here's a proof that I own this public key. So like if somebody calls, send a message to me. Now, that's all that happens for now. And it continuously does this, so like refreshes once in a while. Now when somebody calls it with a public key, what happens is that that person will do exactly the same thing. Will hash the public key, do this query on the DHT. As it's getting closer and closer to the peers, it will find those nodes that the server previously announced to. The message that these DHT nodes will get is just a message that has the hash of the public key, and then a noise encrypted message to the server, so the DHT can't read that. It's fully encrypted with noise as part of the handshake. So the DHT just says, hey, okay, cool, there's a message. It's to this public key. If previously this server said they owned the public key, they also proved it to me. So it's like they couldn't lie. So I'm gonna just relay this message down to the server now. So then the server gets the message. It can unpack it, it's encrypted and encrypted, and then it has some, hole punching data from this peer here. And then it replies back just with a relay message through that DHT, very small, very simple. And then now they have like exchanged the first message, and they do a very advanced hole punching dance that actually makes them connect. Then after that, they're just connected peer-to-peer. So it's kind of like, imagine doing a TCP TLS handshake over a routable DHT in login round trips instead of doing it directly to a peer. That's kind of how it works. So it's like a very distributed TLS handshake. Is he satisfied with that answer?
I think he has a follow-up. So because of the relaying, some amount of connection allowance logic can occur prior to a revealing IP.
So how would you interpret that?
Connection allowance logic. So I imagine that, he gave an example. As in, Bob wants to connect. Is that okay? Yes, here's my IP.
Yes.
The DHT nodes.
Definitely, yeah. So as part of this, and I didn't add this to my example, I can see now I should have. As part of this, exactly what Paul is saying, there's a hook here on the server that when it just gets the incoming message, it verifies that it came from that peer. You can't lie about it. That's what noise gives it. So the server here has a hook that says, hey, there's a message coming in from this person. If you want to accept it, and if you say no there, you won't get a connection. It'll just drop the connection. So you can implement, and there you know exactly who it is that's calling you. So you can implement these very powerful access controls on the network level there. It's basically a firewall inside a firewall, but it's cryptographic. And there you can also say, well, I have, you could even do a thing that's like, I have, I want to have 100 connections max, so I'm going to drop everybody over 100. It doesn't have to be like whitelisting or blacklisting a piece.
Paul satisfied.
You satisfied? Oh, that's awesome. So the cool thing about this is that all this has been released. It's in a release candidate. The only reason why it's not just released, but in a release candidate is obviously we want to make sure there's like very few bugs. We've been testing it pretty heavily with a bunch of people, but you should try it out. It has this cool NPM syntax with 2 ads. So this is living in the DHT layer, this raw API for servers. Try it out, tell us if something doesn't work. Things might not work always at the moment, because obviously we're still hardening a little bit, but it works pretty well. And we're about to release the same release candidate for the Hyperswarm itself that has that API we talked about before with the on-connection and the joins. We have 1 bug left. That's why we're not releasing it today, because we just want to fix this last bug. But hopefully that'll be out on Monday. So it's very exciting. It's basically the same API as before, except whenever there's a callback, there's a promise now. And then obviously we use encrypted connections. But other than that, it's more or less the same. And I'll probably get hammered for saying that, because I'm sure there's details. But pretty good. Very good stuff. Awesome. So next part of the stream is a demo, or more than one demo, and a little Q&A at the end, if people are interested. So I'm going to try to switch back to... No, I should not switch back. I should just go to the demo. Right?
Just go to the demo, yeah.
Yeah.
It should all work.
So this is I think this is my favorite demo in general. Let me just see how big the screen is in YouTube. So
I think you're probably going to want to make that a lot bigger.
Yeah, a lot bigger.
Okay, let's see now.
Delay is not that bad actually on YouTube.
No, it's better.
Beep, 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 beep.
Looks better.
Yeah, that's pretty good. So we had this old tools. Actually, there's a before version of this online on my GitHub, but obviously the first thing we do is like, um, hey, let's use this thing and just pipe SSH over it, because then all of a sudden we can run servers at home for the network, and then whenever we have to fix something, we can just SSH into them. Pretty nice. So we have this tool, HyperSSH, and Andrew has made a fork that upgrades this to V5, but other than that, it's the same. If you're interested in that in general, it's on this GitHub link. But here I can run this, and the cool thing about this is that this 81 thing here, that's actually the public key of our Office server. So I can access my Office server anywhere. The really fun thing about our Office server is that we moved offices into a corporate office park, I guess, and that was first annoying because they had very restricted networks, and then it turned out to be a really good thing because it allowed us to test very restricted networks all the time. So this is actually running on a very restricted network that's like would not work at all with before, and does, like wherever I've seen stuff like that doesn't work here at all also. So let's try it. I'm going to click enter now. And it worked. So you can see here what happened there was it went to the DHT. It did this whole routing thing I talked about before, this login, routing handshake with the public key. It found the SSH server. It hole punched. It relayed that message. They hole punched. They exchanged noise data. And then after that, they were satisfied with that, and it all worked. We're using a UTP connection. I spawned a SSH client on my end, and the server, or Office server, then just proxied that to the local SSH. So this is actually running SSH over Hyperswarm. So it's double encrypted, which is a little bit silly, but hey, gets the job done. So this is just a normal SSH session. So what I can do now for fun is try to run a little server in here. So I should just write it, yeah.
Yeah, just go for it. Just use the code from the slide, maybe.
Yeah, I'll just try to write it because then I don't have to swip. But yes, demo. And we want to get Hyperswarm DHT add next. We actually in the past SSH'd in to upgrade the hole puncher, which is pretty fun. Mm-hmm. It's very circular. So what I can do here now is I'll just do a little light coding, and then if it fails, I can blame it on the light coding. Require the modules, make it HT node. Let's just kind of put it, what's that called? Called a start normally, right? Mm-hmm. Because I can use a little async wrapper. I can't remember the top level await stuff. But we'll just wait for the DHT to be ready, because then we can start by just printing this info here. So this is an API on the DHT that just tells us all the stats that's collected, like the digest of that. And that's why I'm waiting for ready here, because then I know the stats have been populated. So I'll just try run this and see what happens. So you can see this is what's interesting about this network. So the type here is just what our statistical analysis tells us, that it's detected that this port is randomized. So that means that's another word for being very unfriendly. And that's why I can't figure out my port, but it could figure out my IP here. So now you know where we are if you want to come talk to us. Please don't.
Might be cool to mention how the statistical analysis works, just like a brief review.
I mean, it's all open source, obviously, but like the statistical analysis works. Luckily, I'm very lucky to work with much more smart people than I am, and basically, the statistical analysis works by every time you talk to a DHT peer, obviously you're connecting to a peer on IP and port, and then our protocol, every time you talk to them, they send back, hey, this is what I saw your IP and port was. It's a very hard problem to figure out what port and IP am I running on, because there's nets and firewalls in between. So every peer gossips directly with each other what they think the other person's port and peer are. So now the problem is, obviously, one, they could be lying. There's no security here. Even if we had it like end-to-end encrypted, it doesn't matter because it's still a random person you're talking to at the other end. And that could be a troll. So we can't fully trust it, but we can trust the crowd. So we can say, well, we can't trust it completely, but we can trust that most of the people are at least not lying. That's the first problem. The next problem is then, next problem then obviously is like, after that you gotta figure out what's the net type like, and that's where we use this median approach to analyze all the data and, do a bunch of statistics, cut out the odd layers, and then at the end run some statistics that tells us, hey, this is randomized, or this is good. So yeah, I think we can write a little paper around that.
Mm-hmm.
So let me just expand this a little bit. I can just get rid of that so people don't get confused. So what we can do now here is say, hey, let's create a server. And, sorry, my Vim scale's not that great. Key pair. So this just makes a key pair. It's just a ED25519 key pair, like the classic Lipsodian key pair, the key pairs we use in Hypercore. And you can say, listen on that. You can also, obviously, in a normal app, you would have that somewhere else. You would have it on a seeded or something. And then I can get a connection here. Sure, just print out the data and then you can send me something.
Yeah.
So yeah, I'm just printing out the messages, and I'll just rename this to encrypted socket so everybody's absolutely aware that this is actually encrypted. That's how encryption works. And to also here, socket from encrypted socket remote public key. And then finally, because we're just generating a key pair every time it runs, and I should probably print out the public key so other people can connect to me. Public key to string x. So this is a little program that just accepts connections, and I'll run it. So I'll send this key to Andrew. This is the address of my server. Actually, if you're really quick at home, you can also try.
You just put it in the YouTube, yeah.
Yeah. Which is how I do that. Is that this one?
Yeah, right there. Yep.
And back to this one. So now Andrew is going to take that key, he wrote a program, and we'll see if we can connect to me.
Bit of a delay. All right, got it.
So here I got a message from Andrew, and that Andrew saying hello world. And are you on your phone, Andrew?
I'm on the local network now.
Okay. One second. So that was Andrew just connecting to my key. You want to try the other one?
Yeah. We're going to switch networks now.
Yeah. So Andrew killed it. I didn't write here when he kills it, but basically, that gets it's all the classic stream events. So we'll get a close.
Yeah.
So Andrew's going to try to tether now, and we'll try on his phone, his Nordic phone. So the network here in the office, this is running, is like on a core network. That's randomized things. That's what we call an unfriendly network. So Andrew's phone network luckily is friendly. He's just trying to set up tethering right now. It's a little involved.
All right. Might take a second.
Yeah, 1 second. There you go.
Yep.
Oh, you killed it.
I killed it. Yeah, let's try it again.
So that message there was Andrew connecting to me. So he generates a new public key every time. That's why it's a new public key. But this is actually Andrew connecting from his phone to the office server with like hole punching, and this is like the hardest possible. This was not working before. This is like really really hard in practice. And if you're really good at hex, you can see that he's writing hello there. Hey, I guess it's a new line, yeah. So yeah, I know skills. So it's again, it's really really powerful, and that's like Andrew is. It's like a 4-line program or something like that.
Oh yeah, it's tiny. It's tiny. It's it just does a connect and then it.
We can put it up. We can put it up in a gist after.
Yeah, we can put it up in a gist.
Yeah. So yeah, super tiny. I'm looking at it now. Just very cool.
Yeah.
Very cool. I'm gonna kill this program now. So I shouldn't go there. That's our demo. So it's kind of fun because like it's like the demo is just like, oh, this is a little simple thing, and it's just like, you know, oh yeah, that's just the tip of a very advanced iceberg. I should mention additionally, obviously, this is just listening on public keys on your key pair, your own key pair. That's super useful for this kind of stuff we're doing right now. But obviously, like in the hypercore sense, you want to say, hey, I'm a server, I have a key pair, I'm part of this hypercore, I'm in the topic. So the DHT has APIs for all that stuff still. That's called the lookup and announce APIs, and that's what the join method does on Hyperswarm when you use it. So this one still has all that stuff. So here, if I announce, let's see if I can remember the syntax for it. So I'll start by just putting in a random seed here. This is very insecure. Don't do this at home. Just using a seed here that's called seed. So here I can say, I think this is how I do it. You can just fill out the docs maybe, Andrew.
Yeah.
I'll just make this a little bit more clear for the people at home. So this would normally be some hash. I'm just looking at the docs here next to me. I can't remember. So here's how you announce something. You say, hey, I'm this topic. This would be like a hypercore key. Normally, I'm still this key pair. So like create a proof that I want to be joined this and add that to the DHT. And then await that. And if we do that, if we try to run that real quick, let's see what happens if it blows up. So that means done. That means it now announced the server to the DHT. So if I wanted to find people in that topic, I can just do a lookup. I do it like this for cons data of node topic. I think it's like that, isn't it? Mm-hmm. So this is how I do a query to the DHT. Very little nice async iterator. And it's still announced because announce lasts for like 20 minutes unless you want to announce it. Or maybe not. Let's see, I'm just going to look up the API. Maybe I messed it up.
Oh, is there a lookup in there?
No, one second, just looking at the stream. Oh, okay. Did I do something wrong here? Oh, I'll just add the.
Where'd you do that? Oh, you did. Okay.
Was it like this?
Yeah, that was topic key pair nodes options.
Mm-hmm. Well, I'm probably missing something else. It's not important. It totally works if I can remember it correctly. I'll just double check the docs. See, I'm not doing anything.
Constraint no lookups. I think.
You know what? I can't await this one, right? I think that's why. Oh yeah, that's why. My bad. It's because this one is like a query. I gotta do this.
I'll be finished.
Like this, I think. Yeah, right. There we go. So what happened here was I'll just close the door because somebody's cleaning outside. So what happened here was that we did an announce and then we did a lookup, and this is just us finding ourselves saying, hey, yeah, there is this peer in this topic. It's this public key here, and that's ourselves. And then tons of peers saying that because multiple peers in the DHT know that. This is not something you have to worry about normally. This is just the DHT telling us that, and this is what the join does for you behind the scenes. So yeah, that's basically it. I'll switch back to this one. We went a little bit over time because we started a little early, but if you have any questions for us, I'll put hand raised.
Paul has questions about reusing key pairs across multiple sessions. Let's see, let me read that.
Yeah.
So any challenges around that, such as restarting the server with the same key pair? You definitely want to be reusing the key pair on one device.
You want to reuse key pairs for that because obviously that's your address. Think about it like your IP, and like that's so you want to have a secure seed. And we have some abstractions for that we're working on for like obviously not having to record those to yourself, but like you want to have a seed and run it with that one every time. That's like your capability that it's only you that can access that. But no problem.
Yeah, sorry. And if you move that key pair, for example, to private key to another computer, and you announce from that computer as well, so now they're both announcing, it would be kind of a last one wins.
Last one wins, yeah. But the cool thing about these key pairs as IPs is that you can take it with you. So it doesn't matter if your computer at home or if you want to move it to Amazon or you like whatever. The key pairs can move.
But the general model is one key pair per device.
That's the current general model. And then if you want to have multiple things, you publish multiple key pairs to a topic like I did here. In the future, if there's somehow big demand for it, we might consider having like a round robin for many more key pairs. But right now it's one-to-one. Kind of like, again, like an IP. Like there's a server behind an IP. And then, similar to IP, you can have that server then route to other servers, like Amazon does. Mm-hmm. Okay. Is there anybody else?
Anybody else have questions?
In general, otherwise, we're obviously always in the Discord. We'll be doing more of these streams. We love doing this. Next time will be very streamlined because now we have the full setup.
And as for the stuff we demoed last stream, the Autobase and some of the Hypercore updates, we're kind of putting together everything as part of this upcoming kind of testnet release for all these new things combined. And so we're planning on doing that once these networking things are in place.
Yeah. So make sure that everything swarms really nicely on the swarm. But we would love everybody's help starting next week once we release our stats tool to just again get more stats so we can make sure it's just really solid. At some point, obviously, we're going to flip this is still running on something called a testnet, so it has its own separately deployed testnet. You can also help by adding nodes to that testnet if you want to do that, reach out. But at some point, obviously, it's going to switch to mainnet, and it's only going to do that once we have A, good migration strategy, and B, are very certain this is just really bug-free.
And as part of that, there'll be new Bootstrap nodes. There'll be separate Bootstrap nodes for the testnet and for the current v4.
It's already deployed.
Yeah, they're already out.
Testnet is running on -1 on the port if you're curious.
But the beta versions of the modules will just have those coded into it, so you don't have to worry about that.
Yeah.
Question from Gareth about that.
Was that a new question?
Yeah, that was a question.
Oh, we just answered it.
Yeah.
Very nice.
Yeah.
That's awesome. And again, this low-level API we showed, that's just one way of doing it. There's the high-level API that we still use all the time, and mostly use like 90% of the time. That's just like the swarm on connection stuff that's getting released. Hopefully tomorrow we'll just have that one bug. Got it fixed. Very nice.
Do nodes working with the key help routing anything else in the network? So that depends. If it's a client node, like somebody announcing a key pair, they could potentially be a persistent node in the DHT as well and help routing other things.
Yeah.
But typically you'd want those DHT nodes to be running somewhere long living.
I'll have a little comment to that. That's a really good question. So basically the DHT is running its own heuristic behind the scenes. So it's doing all this net analysis that's really powerful. As part of that net analysis, it can figure out, hey, by the way, I'm not running behind any firewall, i.e. like I'm a server online on Amazon or even on a very, very friendly home network that I can just accept connections and I'm a very good network. And also, hey, I've been running for 20 minutes, plus minus some randomness. Then we say that's a really, really strong signal that you just want to be a long-lived member of the DHT. You want to help route the DHT traffic because DHT traffic requires these very, very good peers because that makes the networking much more fast. That's why it was so fast for me to connect to things because the speed is really fast. And this G here it's only like 100 or 200 nodes in the testnet, so it's obviously small, but it's similar speed. So that's all in there now. So if you run this code, even host a server on Amazon, then the server will figure out, hey, I'm a cloud now. I'm going to take on more responsibility running a DHT, and it's very, very little resources. It just happens to be required the network. But if I'm running it on my phone, it's probably going to be like, hey, no, the network is not strong enough. No, I'm not going to do that. It doesn't help the network to do that. It's just going to create more work for the network. That's all in there. So it's very, very feature complete. There's also still APIs like in V4 for storing small amounts of hash data under a key and also storing small amounts of public key data on the keys, which we always like.
Question from Ben. The stream that comes through, is it a one-to-one write and then that'll trigger an on data, or is it split by a maximum UTP packet size, etc.? Definitely would be split.
No. It's actually framed. So it's every message. The UTP, you're completely right. The UTP message layer sends fragmented messages, but the noise reassembles them.
Right.
So wherever you send, it's framed. So if Andrew sends me a message of 500 bytes, I get 500 bytes. If you send me 500 kilobytes, I get 500 kilobytes in one message. There's an upper limit to the framing of its 8 megabyte messages, because that's when the buffering begins to say, that's like a level where I'm like, is this an attack, or is this like just a big message? So that's just or is it 16? I can't remember, but 8 or 16. So other than that, it's all full frame protocol. So if you wanted to write like it's kind of like a web socket in that sense. Like what you write is what you read. Very cool.
So question for replicating V9 hypercores over Hyperswarm V5.
Yeah, we just talked about that today. So you can totally do that right now, but right now, because both layers do encryption, it's to do double encryption, which is like obviously not smart. So we're just gonna add a little patch to that one that makes the Hyperswarm V5 aware. So if you notice it's running on V5, it's not gonna do the double encryption. And then we can run the entire thing on the same thing, which is obviously really nice and what everybody wants. You could just write it. You could just run it today, and you would just get double encryption, which it's not the end of the world. It's just like wasted CPU. But that one shouldn't be too hard. So I think hopefully we'll have that out early next week also.
What are the really, really powerful use cases that Hyper is interested in? I think the sky's the limit with a lot of these networking things, because the ability to have any home computer be a server is just it's such a novel idea, and I think that opens the door to to lots of new privacy opportunities and just the ability to kind of set up services with very low friction and make them available to small groups of users and then gradually scale them as you go. I think this technology in particular is really good for that.
Yeah, it's all about bringing the cloud home. I think like for us, it's like saying finally with these kind of capabilities, we're back to a stage where home servers can compete with everything in the cloud. There's like no way you can, if you have a friendly network, you can serve the entire thing. Like there's no reason why you want to have to push everything to cloud. You can if you want to scale, but you can start there, and that's what we're all about. The ability to start at a scale where it's like, it's just my computer hosting things, so it's just my Raspberry Pi hosting things, and then you can scale up from there. And then also like just, I gotta say, like I've been incredibly amazed at the usefulness of this SSH parts we've been doing. Like just running these small programs, no VPNs, no anything, but we can get connectivity from anywhere to debug any problem at any time. It's incredibly powerful, and very looking forward to when that realm expands into way more things. Cool. Very nice. So I think that's a good note to end on. Yeah. So thanks so much for tuning in. We love getting the questions. Sorry so much for the messy setup, but next time will be much more aligned because we got it all set up. Thanks so much to Paul for helping us live debug that. It was very, very useful. I don't think we would have gotten it working otherwise. If you have any more questions, we're in the Discord. I'm always lurking in all the channels, and right now I'm lurking especially in the Hyperswarm one. We love to get more feedback and help, and we're very excited about it. And again, this is all out and a release candidate, so try it out. if you want to, or have any comments. There's also going to be obviously a spec for this, so we can get it in other languages and get it reviewed. But it's really good stuff, if I'm allowed to say that myself. So yeah, thanks again, and talk to everybody soon. There'll be a new dev stream in probably a month. So yeah, see you. Bye bye.
See you, everybody.